I'm Sarah, Groff, Hennigh, Palermo. On Twitter, I'm super SGP, so if you like the opinions you hear here today, there's way more of them on the internet. So up until very recently, I was an engineer at Kickstarter. I left about a month ago to have a career crisis and find myself, but that's what I used to do. When I'm not coding for money, I'm actually coding for art. I do live code as well. Those SVGs I make with ClojureScript, handmade artisanal SVGs in Brooklyn. And I'm really excited to be here today to talk to you guys about errors. And I have a lot to say. I realized, by the way, when I was writing this talk, that it's actually like 4 talks. And rather than make it shorter, I just decided I was going to talk really fast. So if some of the slides go by fast, you don't read the code, don't worry, it's going to be on the internet. There's lots of links with like details, so you can see it all later. So let's get started. Lately, I've become super interested in the way that we approach errors as programmers, as a culture. And I wasn't going to start off telling you why I got interested, because I feel like it's a little bit incendiary. But I decided I'm just going to go ahead and tell you now, and hope that you'll keep listening, even if you think I'm kind of insane. But I'm interested in errors because I really hate types. And I know that that's not like a really popular opinion here in 2018, right? This idea that I, as someone who only knows some programming, think that like I know way better than all these computer scientists who have done research and have told us that types are like the way to do it right. But I know that type errors are real, and so I was like, well, if I wasn't going to be into these, how am I going to have a better way to approach errors? So I decided to do some research. And luckily, errors are really interesting. On the one hand, they're this cursed object that explodes rockets, overdoses people on radiation, and makes web forms refuse to submit when you need them the most. And as such, they're a danger around which every right-thinking person is furiously erecting fences, right? But on the other hand, errors are kind of hilarious. So consider the case of nuclear Gandhi. In the very first Civilization game, for some reason, towards the end of the game, Gandhi would suddenly become incredibly aggressive and start threatening to nuke everyone, which, if you know Gandhi, is kind of unlike him, right? So it turned out that aggressiveness was represented with an unsigned byte, and when Gandhi's was set to 1 and the player took an action, like adopting democracy, that made it drop even further, it flipped around to 255 and gave Gandhi max aggression. Players liked this error so much that Civ still uses it, even though the mechanism has obviously been discovered and understood. Errors can also make us inventive. So in Wing Commander, the game threw an error when you completed an out-of-memory error. And the programmers could not figure out why it was throwing this error. But you know, sometimes you just got to ship. So they changed the error message to a message of congratulations and just went on with their day. Errors can also be delightful. So when I was working on my live code framework, doing some animations, I forgot that rotations needed to be stateful from frame to frame. So I accidentally made this shaky circle friend because it restarts the animation every 50 milliseconds. But it's one of the most popular effects. People love it when I use it in shows. They're always like, that circle's so cool. So, you know, and then I broke that once and made this other really cool rotation that fixed the thing I broke. I don't know, I thought they were both pretty cool. To our credit, as programmers, we recognize that errors are an inevitable part of our culture, right? We've all identified with this dog. Sometimes we feel this way about CSS. You know, we resent those movie astrophysicists who can save the ship while we get a bunch of nans. We have complicated relationships with code, and we all know our own call of the wild. And so errors can be terrible, and they can be hilarious, and they can be amazing. And maybe if they're terrible, we should just cool it and not worry about what we're missing out on. But you know, something I noticed is that examples of interesting errors come from things like games and art, and bad errors come from things like healthcare and rockets. But fortunately, as web programmers, we're much closer to the former. even though as a culture, we tend to act as though we're the latter. And we rarely think beyond how to fix errors. And it's not really a big surprise, actually. So culturally and philosophically, we're trained to deny and avoid error in pretty much every aspect of our lives. As Catherine Schultz tells us in her book, Being Wrong, which, by the way, is a book when people see you reading it, they all want to talk to you. This view is really common, and it's very popular with a number of heavy hitters in history, Plato, Thomas Aquinas, and it comes from the idea that errors are a product of a gap between the true world and our flawed human minds as we attempt to interpret it. And this is kind of the view that gives us a yearning for correctness. However, there's also an optimistic view of erring. And in this more modern view, originating in the Enlightenment, the idea is that this gap is the result of imperfect perception, but it can be faced and overcome as we asymptotically move towards truth. In fact, seeing the world perfectly as it is might not even be the right goal. As Schultz writes, seeing the world as it is not is pretty much the definition of erring, but it's also the essence of invention, imagination, and hope. This gap may also just be the downside to our massively great inductive reasoning upsides. All the shortcuts we take that make humans such good thinkers, inventors, planters, some like intuitive little plants, right? All of this means that sometimes we misperceive. So maybe we can risk it up. So I'm going to talk a little bit more today about what we mean by errors, how we deal in JavaScript now, situate that historically, and then go ahead and see what other options might be available to us in the future. So what do we mean by errors? There's a lot of different schemes that people have come up to answer this question. A lot of the times, they split along the lines of whether it's an avoidable programmer error or an unavoidable universe failure, sort of like we see here from the first edition of Eloquent JavaScript. I think that's not the most helpful way to look at it, because as we've seen, if errors are inevitable to us as humans, then that's just as much a universe failure as anything else. So the framework I like comes from slips, mistakes, and failures from Thomas Petracek. And this is by sort of the magnitude. So slips are where your idea was right, and you tried to encode it the right way, but you made a syntax error or a typo. And I always think of these as errors that we don't really ship, because they break right away, the linter catches them. At the other end of the generality spectrum, we have mistakes, where you made an error thinking through the specification. And that's really fuzzy, like what does specification even mean? But I just think of a mistake as building the wrong thing. In the middle, we have failures, which is where you had the right idea, but encoded some part of it poorly. And this is what we're most concerned with day to day. So how do we deal with these failure-type errors in JavaScript? JavaScript uses a type of exception handling that's about half the original system used in PL1 in 1968. There's PL1 up there in the language family tree, descending from Fortran and Algol. In JavaScript, exception handling arrived in ES3 and worked pretty much as it still does today, right? We have the error prototype to construct errors. We have the keyword, we have the throw keyword to propagate them. We have try, catch, and finally to create a new lexical environment to handle the exceptions, and then to clean up after their mess, whatever can't be fixed by resetting the lexical environment, you can use finally to clean up. One thing that surprised me in my research is there used to be a non-standard multi-catch syntax. So instead of having to put a conditional inside your catch, you could just do catch, 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 catch. But that's not been there since Firefox 59, so that boat kind of sailed. In addition to user-defined errors, there's 6 built-in error types. Only 5 of them are still thrown. Eval error just exists for backwards compatibility. The biggest change to error handling in the spec arrived in ES5 with early errors, which is mostly used for strict mode, to be sure the heap is not littered with landmines, which is to say there's no code in memory that's not going to execute, and to disallow code that would otherwise be allowed by the grammar. But these are reported when the program is evaluated, not when it's run, so it's not part of our exception handling scheme. Inside the exception handling system, things are pretty much as they are in most other languages. But in this case, common is definitely not a synonym for optimal. When the invoking function is able to use catch to respond to an error, the stack trace is available, but the invoking function cannot affect code anywhere down the stack from itself. So consider this example. There's this parse entry function, which throws an exception when it can't parse a file. And it's getting called 4 functions in 2 lines deep. Maybe it's inside a library, and this analyze all files is in your code. When it fails and throws, we might, as programmers, actually have an idea, say, of a good default we could use to continue, so that the parsing could keep going and we don't have to unwind the loops. And maybe if only we had a default, right, we could rewrite the function to account for the fact that you could return a default value. But I think you can see how making this the responsibility of this inner function both breaks encapsulation and could quickly get out of hand if you had ideas for other sorts of interventions. And so we might be able to do something, but it doesn't matter because it's not possible without preprocessing the data or rerunning the entire function. Other changes to exception handling have come, obviously, in JavaScript with promises and async await. These haven't changed the basic concept, though. They've extended it. They've made for some interesting corner cases and variations. For instance, if you return from a nested finally, you're never going to call your outside handler, so we'll never print banana, which is very tragic. Errors may also remain entirely uncaught by a chained catch. I didn't realize this until I was messing around, but that first promise isn't going to be caught by the catch. There's a proposal for promise.try that would address this, but currently that's a big sticking point. Then with async await, the variations and pitfalls increase further, as my friend Francis found out. He had a fun bug where using this function, log stats was being called twice, and then throwing an error. He wasn't sure why. It turned out that an external function used by log stats was throwing and being caught, which surprised him because he was just thinking of that for the await. So he came up with some solutions. You could just only wrap the await in a try block, which is what a lot of people have done. If you have a lot of async, it leads to a ton of trying, obviously. You can use the goify pattern, where basically you create a promise that returns an error data tuple, so then you're handling errors on a per promise basis. Or he changed the catch, but as we discussed before, this won't actually catch if the promise throws. So there's a lot of variations with implicit pattern trade-offs, but at the base, it's the same try-catch mechanism. Finally, it's also worth noting before I go on that the DOM does provide error event listeners, which look really interesting. I've never seen them used in production, and I didn't even know about them. So if anyone out there is actually using this, please come talk to me, because I'm really curious how you're doing it. So basically, this is JavaScript's fairly unexceptional exception system. It has some funny little corners, and on the one hand, it's super unremarkable, and yet it seems strange that such a remarkable language, built to be so dynamic for all of the good and ill that that implies, and bound strongly to its earliest choices through its commitments not to break the web, should have what amounts to a kind of anemic way of dealing with errors. And it's this lack of balance that I suspect sometimes leads to JavaScript's reputation as a problem child or a foot gun. And lately, the answer to that has been to dial down the dynamism. But as I've mentioned before, I'm not super into that solution. So I've written and spoken about this a little bit before. If you're interested later, DM me. But the short version of the argument is that the choice to pour our limited engineering effort into a totalized static typing system for JavaScript, both in tooling and in day-to-day product engineering, is a mistake. Type checking only catches type errors, and there will always be points of failure in an application that deals with networking, user input, and the DOM. One of my proudest type-based achievements is I've actually thrown a runtime error in Elm, which people claim is impossible, but it turns out when you're appending strings to the DOM, no one can really save you. Also, though, maybe being saved isn't so great. Maybe being so correct forces us to create huge, unwieldy systems, and being small and composable makes your programs easier to understand, even if slightly more error-prone. Maybe working with computers in a tight iterative loop is just more pleasurable. And maybe looking at computers as conversation partners instead of as half cop, half servant is better for us as human beings. And these are all good reasons to give error handling a second look. And there's also, I think, a political and aesthetic reason to move away from solution through specification. The idea that the best way to be safe is to make being unsafe illegal has deep roots in computer science's positivist history. But this approach blocks out the strange, the hybrid, the human. It prevents us from discovering weird mistakes like shaky shapes. Politically, it also harms us by insisting that only strong categories are valid and denying liminal spaces, which is to say complex truths. Right? Consider the US Census. Up until I was 20, you were only allowed to pick one race, because that's what the system could handle. But that's not true. I am not one race. Like, that's not the answer. And it took more work and the acceptance of looser categories for the system to even reflect some portion of that truth. The same can be said for gender identity, right? There's not two answers, there's not four. So the idea that we should restrict ourselves to communicating in a way that machines can understand instead of like working to make them partners seems to me like the path to a pretty barren future. So I'm going to tell you about errors in history, right, and see where we really came from. If we arrange general error handling methods from the dramatic to the subtle, and this list comes from Chris Hauser, exception handling comes right in the middle. At the top, the most dramatic option is to just crash. This is obviously the original classic, direct from Fortran. And it makes sense when a computer is a glorified calculator and you have a knowledgeable operator sitting right there, right? Why keep doing calculations if they're going to be wrong? Crash and fix it. But in modern times, this can be anywhere from inconvenient to really terrible. So for instance, recently, the New York City subway replaced some signals, including a computerized signal. And it turned out that the switch had a bug, and the only way to work on it or to fix it was to reboot the subway, which took a really long time and was incredibly inconvenient. So in this case, just crashing was probably not the best idea. Between just crashing and throwing an exception is the idea to enter a debugger, which you might be familiar with if you've used Rails very much. Right? On a Rails dev environment, if you throw a bug, you can enter the debugger. And those switch engineers maybe would have appreciated this approach to rebooting the train. Less dramatically, you can return a special value. This approach is pretty uncommon in modern languages, except for some utility functions, right? Find index will return -1. And callbacks, where error is passed as the first value. This approach suffers from the semi-predicate problem, which is to say that you have to check for it explicitly. That's its biggest downfall. Even more deprecated as an approach, and one of the first solutions after just crashing, is to set an error flag. This was common in things like BASIC. And I think you can see how like setting an error flag would lead to returning a value, would lead to throwing an exception, even further outside to help the system deal with it. And then finally, we have the least dramatic option, which is to recover and keep going. And sometimes this seems a little ridiculous. Why hide errors? Only terrible things will happen, and they will be so hard to debug. But context and possibilities for recovery really matter here. This is what HTML does, for instance, right? Like maybe you didn't close a tag, but you can still read the text. And even though it can seem impractical, there are times it's the most practical. So I learned from Wikipedia when I was working on this that the default IEEE 754 floating point exception handling behavior is to resume computation following the substitute of a default value if you have an arithmetic error. And this actually would have prevented the 1996 Ariane 5 explosion, which was caused in part by the fact that Ada just aborted computation on an arithmetic error like an integer overflow. Finally, we can add a few other elements to the list of ways we've historically dealt with errors. You can send a signal, which is a little bit different from a return value, because anyone can listen for it, but you're not throwing it. And there's option types and maybes, which could possibly fall under keep going. Some approaches can be seen as a combination. So Erlang is basically signal plus crash plus recover. And that's sort of where we are. But let's look at where we could go. This is the last section. There's a lot of different routes we could take to expand our approaches to errors and adjust our relationships to machines. And as I think about where I want to see computing go in the future, I keep coming back to this tweet from Amelia McNamara about a talk Brad Myers gave at Dogstool, contrasting, traditional programming language goals, correctness, performance, to new ones like modifiability and learnability. In particular, I always think of errors or a better error handling method as involving these last two, modifiability and learnability. To get there, we might focus on things like more robust ways of dealing with nullability as it exists today. And that's coming, right? There's the optional chaining proposal that I think is in stage 1 that would by reducing the number of checks for small quotidian errors, free us up to focus on exception handling. And that might pair with expanding ways to work with errors as events or focusing on good default arguments. Focusing on defaults leads us into a more broad look at robustness in addition to rigor, which is to say looking for things that will bend and not break, that makes recovery more possible and less disruptive. This might look like augmenting or rebuilding the current exception system. Remember when I mentioned that JavaScript's exception system is only half a system compared to PL1? So as described in the canonical exceptions paper from 1971, exceptions and exception handling mechanisms are not needed just to deal with errors. They're needed in general as a way of conveniently interleaving actions belonging to different levels of abstraction. They're not necessarily rarely activated. And so this involves moving responsibility up the stack, but not necessarily unwinding errors, which is to say context is maintained. It proposes a specification for exceptions that have 3 types: escape, signal, and notify, which can require termination, be the caller's choice, or forbid termination. And it's these capabilities that were hacked off from C++ due to the determination back in 1989 that since no one really used them in Cedar Mesa, nobody should ever have them in their exception handling system ever again, basically. If we wanted to leave the past in the past, a focus on robustness could be a focus on maintaining good state in the face of user interaction. For instance, I use Figwheel for live code. When I make an error, it actually just keeps the last good state going while telling me that I've created an error. React's error boundaries also do the same thing. And if you can imagine sort of combining this insistence on maintaining good state with the ability to access a production REPL, right, we could do all sorts of crazy good live fixes that wouldn't hurt users. What would continuous deployment be like if you deployed an error, you identified it in the REPL, you made a hot fix in one restartable module, right? Like, that could be a really amazing way to go back and forth with your system when you define errors. Then, if we got really crazy, we could look at stealing good ideas from even further afield. One is recovery blocks. So this is a pattern where you create an acceptance test. You give a list of ways to attempt a successful result. And then if all of those fail, then the error is thrown. And this, the acceptance test usually can access variables from before and after the functions are run. So that works for pre and post conditions or domain and range errors. Another option would be to look at algebraic effects and handlers implemented in things like F. This handles errors in a monadic style. If you're not familiar with OCaml syntax, this might not make a ton of sense. But the really important part here is that K, which is the continuation. So you can intervene and then pick up where the language left off lexically. Finally, we could just head for the stratosphere and consider ways to reframe our relationships with computers. We could make computers a full partner with program slicing and better automatic suggestions. The Rosette language extends Racket to use solvers and synthesize code. We could also take the alternate approach and work to reframe computers from something that just works to something that may be tinkered with and grown and might not be just this machine for brutal effectiveness. And some of these seem really big and really fast and very undetailed, but it's only by wanting more that we're going to get explorations into getting more. But there is something we can do today, and that's to make it culturally acceptable, even encouraged, to spend time thinking about ways to fail well instead of just trying not to fail altogether. And so in terms of encouragement, I have one last quote from you, again from Being Wrong. We want to turn away from error because it reminds us of our existential despair, that we're separate from truth and from one another. But also, the only true way to engage and to create and imagine is to risk error. So let's not cut ourselves off at the knees by underestimating ourselves and our machines. Maybe let's not be afraid. Instead, let's make it safe to take some risks and throw some errors, and then to continue. Thank you guys so much.